Judy. Just to preface this, it's become apparent for some time that the things that we're doing in laboratories, or the vast majority of laboratories nowadays, still involve a lot of manual collection and manual observation. And these things are still very valuable, and there's still a lot of skills to be learned and a lot to be learned from the animals. But what we're actually starting to understand now, as we go further into the 21st century, is that what we're doing in vivariums and how we're handling laboratory animals has a fairly profound effect on the quality, not only of the experience of the animals when they're in that vivarium, but also the quality of experiments that we might run down the line, in terms of function, in terms of cognition, and in terms of behavior. Essentially, anything that we're doing in the vivarium can cause disruption to the animals. And until very recently, we didn't know how long that actually lasted or what that effect actually was. One thing that was actually very important to us was that the cage site assessment, just in terms of lab resources, if you have a lot of animals in the laboratory, or even only a few animals, cage site assessment is still very, very important, both from a veterinary health point of view and also from the technical point of view, to make sure that the animals are functioning and acting as they should. But cage site assessment, due to a resource issue, only occurs once or twice a day. The ability to monitor animals over a 24-hour period, 7 days a week, would be very, very valuable. Up until very recently, this has been very challenging, and equally challenging to be able to do it in a group-housed environment. The ways that we handle animals today in laboratories, we're learning a lot about that, and about how the best way to handle them is. Essentially, any way that we handle animals and interact with the animals disrupts their day. And that, again, can have a fairly profound effect on studies that occur down the lines, particularly those studies when we're dealing with function and behavior and tasks that need to be completed, and when we're checking for cognition. So the handling of animals has been shown to have a fairly detrimental effect if we do it the wrong way. But even if we do it the right way, interacting with the animals is not something that we like. So when we look at how we monitor animals currently in a vivarium environment, we're only getting a snapshot in time with that cage site assessment. We want to know more about the animals, and we want to know more about what's happening when we can't see them. We want to know how they interact with each other, and we want to look at the causes of injuries and unexplained deaths. So very often the anecdote is that a technician comes in the morning, and you see that there's one less animal in the cage. One animal has expired. We don't really know the reason for that in a lot of cases. And it would be very good to be able to go back in time and be able to look at that. But as I said, a snapshot in time is essentially what the cage site assessment is. So we want to be able to monitor animals longitudinally, 24 hours a day, and look at those cases where the animals are actually suffering, or when we can assess them at those times when they should be interacting socially. We want to be able to look at what is the normal behavior of an animal in its home cage environment. The motivation for the system that we have brought out is essentially the things that I've just mentioned. And rodents are social animals. Isolation is stressful for them. The interaction of the laboratory staff, scientific staff, these things are all stressful on the animals also. Again, they're predominantly nocturnal, and we would really love to be able to see how these animals are interacting with each other, what kind of behaviors they show at night when the lights are off. And we want to be able to, from a quality point of view, establish baseline behavior profile. So before the testing, we want to know, is this cohort of animals acting the way cohorts of animals of this type should be acting? So are they conforming to that phenotype? And then during the study, we want to be able to look at the effects of the handling on these animals, of the tasks that we're making these animals perform, and we want to find a way to understand if these animals are actually staying normal. And then from a surveillance point of view, we want to be able to look at welfare monitoring. So the indications of adverse effects, is there a possibility that these show up sooner if we're monitoring the animals at night, if they're the things that when there's no one in the room, when there's no technicians interacting with them, do we see indications of adverse events? And this is actually something that's coming to the forefront now in laboratory animal sciences. The handling of animals and the surveillance of animals and the ability to monitor welfare without doing those cage side assessments. And there's been a lot now over the last few years published in this area. It's a particularly fascinating area. And I think that the quality issues where the effect of the environment on the animals and the effect of handling on animals and how that impacts downstream studies in cognition, in behavior, I think that that's very important, and that's something that we are continuing to look into and continuing to refine ways to pull data from that. And overall, it's a quality control issue within laboratories nowadays. So there's been a lot of publications on this, and there'll be a lot more. And at the end of it all, you have the automated cage ethology that's springing to the front now. And there are various devices out there, various technologies that want to study the behaviors of mice. These want to look at it, as I said initially, longitudinally. But there are fewer devices that are actually looking at animals in their social context, in their home cage. So a lot of these are task-oriented. The animal is still working in isolation or living in isolation when it's in that environment. So it's probably more valuable and probably more true to the actual phenotype to keep the stress levels of the animal down as low as possible and to look at them when they're group housed and to have it in a typical cage so that when things like cage changes are made or when technicians are interacting with them, the environment isn't overly different. If we can control that, then it stands to reason that we can have a better control downstream when we're actually running a lot of the task-oriented assays that we would like to run in cognition and behavior. So in 2011, along with the Mary Lyon Center, the Mouse Research Center at Harwell, the MRC, the University of Edinburgh, and Actual Analytics, in conjunction with sponsorship by the NC3Rs, took up the Crackit Challenge. And the Crackit Challenge was created to address some of the concepts that that I've alluded to previously here. So in a regular home cage, essentially any cage in any vivarium that was IVC compatible, to maintain the social housing of animals so that they wouldn't be in isolation with very little impact on husbandry, and to give us a 24/7 insight, so a longitudinal insight into what was occurring in the home cage, minute by minute, second by second, day by day, month by month, if it had to happen. And on top of that, we looked at how many key behaviors would we be able to start to analyze automatically through a form of machine learning in the home cage, in that social environment. And from that came the Actual Analytics home cage analyzer. It consists of an RFID chip. You can see there, it's very, very small. Fits into either the flank of the mouse or a pouch in the stomach, or it can even go into the back. It doesn't affect the mouse's gait or the mouse kinematics in any way. There's a computer and a camera, and you can see that the cage that we're using could be pretty much any IVC cage. The setup itself has 360 nanometer or 860 nanometer LED infrared lighting above the cage, and a PC Core i7 with an HD-ready 720, 25 frames per second camera. So we're monitoring essentially 25 frames a second, 24 hours a day, 7 days a week. And we're looking at those behaviors that are occurring in that home cage in the social setting. And it's actually quite interesting what we get from it when we look at what's happening in the light phase and what's happening in the dark phase, and particularly when there are no operators involved. We generally show a video at this point, but we won't. But what you can actually do here, and what we're actually showing, is that you have an automatic identification of each mouse at each position in the cage, and a catalog of behaviors that those mice might be carrying out, whether it's nest building, drinking from the water spout, feeding from the hopper, showing aggression towards each other, grooming. So there's a various catalog of behaviors. The machine learns those behaviors. It creates a classifier, and then that starts to automatically be tabulated. And at the same time, you're measuring from a base plate. So you're measuring the locomotor activity, and then there's an algorithm that brings that together with the camera, so that if something were to occur, say in the middle of the night, that was unobserved by an operator, you would be able to flag that. The system would be able to flag that for you, and you would be able to go and actually witness what happened at that point in time. So what we've actually started to see is that certain phenotypes that are known not to be aggressive when they're housed together do actually get quite aggressive in the dark period, or they do actually get aggressive in the light period when there's no operators around, or vice versa. We see nest building in some animals where there wasn't supposed to be nest building, that didn't happen when it was being observed. And essentially, the most important thing is we can actually see the social interaction. We can see how these animals are interacting with each other. We can see the social hierarchy within the cage itself. And that comes out both in the automated analysis and in the ability to annotate specific pieces of video and go back and analyze those specific pieces of video. So interpreting the baseplate data, the baseplate works in concert with the camera. If we were just looking at locomotor activity, we would see something that you see in the bottom left. Essentially, it looks like a whole lot of lines going across a checkerboard. But what our machine is actually showing us is what you see on the top left. If we had an observer from the top down looking at it, they would be essentially drawing something that was close to that sort of the filled line, the filled blue line, and the filled green line. But when we actually have the machine doing it, the machine learns to do it quicker and quicker, and we have what you see as the sort of the unfilled line. So when we do the valuation, we manually annotate the position of each animal every second. And then the machine learns that, starts to do that, and then it calculates the distances that the animals are moving, and that correlates the distance. So that's from the camera, and then that correlates that distance with the base plate. And as you can see from the graph on the top right-hand side, as the machine learns this, it gets better and better, so that eventually the machine begins to observe the animals and track the animals, again, 24 hours, 7 days a week if you needed it, in a way that is significantly better than a single operator, and even more significantly better than two operators doing it. And this gives us a good idea of social interactions between animals. And this slide that we're looking at right now, again, with a video, we would be able to sort of show you this, how the video looks for this. But regardless, the statistics that come off from this actually can, because it can identify each animal individually, we can look at the amount of time that they spend interacting with each other and the amount of time they spend away from each other, along with the distance that they spend away from each other. So that gives us one idea of the social interactions in the cage, and also gives us an idea of the overall hierarchy within the cage. And this actually becomes quite important from a husbandry point of view. It also becomes important from an animal welfare point of view, because when we see animals that are underweight and we don't quite know why, or we're looking for drug effects, or we're looking for resocialization effects in some models, or resocialization after we've extracted an animal and gone and either scanned it or put it in another assay where it might have been isolated for some time, the resocialization is actually very important. And some animals don't resocialize right away, and other animals resocialize immediately. So we can actually see if there were any detrimental effects of subsequent assays on these animals. The next slide actually shows that, when we move animals, so we have a graph, you have 3 graphs here. You essentially have 3 different strains of animals. Each line in that graph is the amount of activity over a 48-hour basis. You can see the light cycle and the day cycle, those are cut up into 12-hour sections. You can see immediately, empirically, that you have a lot more movement in the dark cycle. That's to be expected. But what actually comes out of that is what you see under the red arrows, that some animals handle disturbances or anticipate disturbances like movement in the vivarium, cage changes. Some animals actually anticipate these better than other animals. And some animals actually continue with more actively into the light phase than was previously known. So the end of this active phase at lights on depends on what strain you're dealing with. So we start to see very discrete differences between strains and very discrete differences between what's happening. The circle up on the top left-hand corner is essentially a cage change. So this shows you how the animals are reacting after the cage change and how long they will react to that cage change. So it would also be able to give you that quality control measure that you could take into subsequent assays. So if your animals are not quite settled down, if this circadian rhythm is in some way disrupted, if there's been if you've had an acclimatization period that hasn't been long enough once the animals have entered the vivarium, then you'll actually start to see this quite visibly on your computer screen. And it's easy to parse that out. It's easy to find individual animals that aren't reacting the same as other animals. And it's easy to see animals that aren't socializing in a way that we would have thought that they would have. So it's possible, just from looking, that cage-side checks are not actually showing us everything that we see. So they don't recapitulate that undisturbed cage. And we can only check those cages so often in a day. But what you're actually seeing here is a trace of that motion over 48 hours. And you're seeing how active those animals are. You can see, obviously, that during the light phase, there's a lot more downtime, and then there's a lot more active time. And you can see exactly how active those animals are during that phase. When we look at stereotypical behaviors and hyperactivity, and especially in terms of endpoints, what we're actually showing here is you have 3 separate animals. There's the blue lines, the green line, and the red line. And you can see that the red line, the red circle animal almost immediately is showing more hyperactivity during the dark cycle, and that carries on over a few days to the point where it's really moving a lot during the dark cycle. And during the day cycle, you can see that it's slightly more hyperactive, but not something that would stick out from the other animals in the cage. When we look at it closer, and we check the cage, we actually start to see that at the time we checked the cage, the animal didn't look hyperactive at all. And if you look at the subsequent cage checks on day 2 at the same time, that animal itself isn't showing any different than any other animal in that cage. Yeah, at those times when we're not checking the cage, as we move into the dark cycle, that animal is incredibly hyperactive. So whether this was drug effect or whether this was simply an animal that was not conforming to the phenotype of the other animals in the cage, or whether there was something that was wrong with it centrally, we had still gotten to the point where, you know, at these checks, at the end of those checks, we had hit the humane endpoint for that animal. It was moving stereotypically in a way that just wouldn't allow us to use it in further studies. We probably could have intervened earlier with that had we been able to look at what was happening during that dark cycle. So if you look particularly again at day 1 and day 2 at the dark cycle, you can see that that animal is acting differently than the other animals in the cage. So the consequences of not knowing that would be putting that animal into put some functional or behavioral assays and having that have an effect on the end results from those assays. Here's another example of what we're seeing from the observations. So again, if we're looking at these animals continually throughout the dark phase and throughout the light phase, we see that with this this group of 3 C57 black 6 males, we have roughly 25 cages. So all of those numbers at the bottom are separate cages. And we can see that we have one hyperactive subject in one cage, and that animal is actually pulling the other 2 with it. So that phase, in the light phase, if we had checked that cage, we wouldn't see anything abnormal. But during the dark phase, we can see that it is an extreme outlier. And not only is it an extreme outlier, it's also pulling the other 2 animals with it. So one hyperactive animal in a cage that we can spot is essentially creating the other animal, or creating that environment to be relatively unsettled and pulling those other animals with it. So if when we remove that animal from that cage, we actually see that the hyperactivity, or the level of activity in that cage along with the other animals pretty much settles down. We're particularly interested in being able to look at welfare deficits, and we looked at, or the MRC and some of the other partners looked at a group of animals, or different groups of animals that had different phenotypes. In this case, we had a good example from a specific neurological mutant. That animal, you can see, is in the center of the screen, kind of lying on top of the tube. Now, if you look at the distance traveled in the top left-hand corner, you can see the light phase and the dark phases labeled. That animal itself is the animal that was traced in blue. During the day, we don't see any differences in the interaction that it's spending with the other animals, so it's interacting fine. But we see at night that the amount of time that it's not moving is actually significantly different than the other animals. So our trace in green pretty much shows a single animal through the dark phase, and the trace in red and blue are the other animals, and the blue animal itself is the one that you see in front of you most clearly, and we can identify the fact that that animal is actually quite sick. So simply after a 24-hour trace, we can see that were we to look at it in the daytime, examine it in the daytime, it would be fine. But were we to look at it over 24 hours, it is interacting with animals a lot less, and it is also moving a lot less than the other animals in the dark phase when it should be moving just as much as the other ones. We can find social isolates. So in a particular mutant for social isolation, we can see that the interaction between specific animals, and this is being done automatically, it's giving us this interaction between that animal and the other animals and the other animals in the cage and each other. And we can see that the wild type A and B interaction, both day and night, is significantly higher, but the interaction between either of those animals and the social isolate mutant is significantly lower. So that's conforming to phenotype. We can detect that phenotype, and we can spot, and in both this case and in very many other cases, we can spot that animal that is the outlier. We can spot that animal that has a different phenotype than the other animals. So the ability to label animals discretely and to be able to identify each animal and each behavior discretely over time and distinctly over time is very, very important. And we think that this is actually essentially giving us a very different view of the dynamics both within the cage and within the vivarium and between operators and the animals than we've ever really had before, particularly when we've been dealing with animals that were in isolation or when we were only checking the animals in their cages, in their home cages, once per day or twice per day. So again, this is the kind of graphical readout that you get. We had established that that there was a lot less interaction between the mutant and the other animals, and this is what it essentially looks like. So you can see from trace C that you have a lot of interaction between animal 1 on the top row of trace C and the second row of trace C, but virtually no interaction between those two animals and the third animal on trace C. So during the dark phase, the social isolate, the mutant, is keeping itself very, very far away from the other animals. Again, a video shows this a lot more succinctly. So I'll just describe it for you. The animal there is labeled. You can see it's got its individual label. We can tell that's the social isolate. And the other two animals are essentially underneath the hopper. And it keeps itself at a considerable distance from those animals pretty much all the time. We also now have the opportunity to look a lot deeper at novel behaviors and also to be able to do things that we formerly looked at in animals in isolation. So things like rearing, nest building, climbing, drinking, eating, social transmission, preferences, aggression, grooming. We can have that recorded for us, and we can have that actually telling, the machine is actually telling us how many times the animals will do these on a daily basis. If one animal stops doing it, it'll give us the social distancing between those animals. And we can actually start to see that a lot of the behaviors that we would have normally seen in isolation, if we take the animal out, take it to a different room, look at it in isolation, those behaviors manifest themselves significantly differently in the home cage. And what we're actually doing with that is creating a repository of exact terms for what is happening, what is the condition of these animals, what behaviors are they actually manifesting, and then we're making informed decisions about what assays to run. Are these animals capable? Have we met the ethical endpoints for a certain animal? Or are the conditions in our vivarium suitable for these animals? And that can change from transgenic to transgenic, from mutant to mutant. But the fact remains is that we're thinking about it now from the animal's point of view. What is actually happening in the home cage? What is the social status within that cage? And how is that status affecting the welfare of the animal? And how can we intervene if we have to? Here is another slide that shows actually the the philosophy behind the system, as well as mechanically how the system works. You have a blue tracing, which is the baseplate tracing, and you have the green tracing, which is overlaid on that. That is the tracing from the camera. And both of those go hand in hand. And what we've got here is an animal who's on one of the cage features is standing up to eat from the hopper. So the base plate is no longer measuring it. But when we looked at that, and if we spread that time out, you'd see it was a fairly significant amount of time that it spent on top of that feature. We didn't see any base plate data. But because the camera is recording and because the algorithm works in concert with the base plate and the camera, we can tell that it's not no motion for the animal. The animal is actually standing and eating. So we go back to that point in time and we look at that particular piece of video and we see the explanation for why we suddenly got no locomotor activity data from the base plate. And I think that's actually a particularly valuable feature of the system, is the fact that you're not simply recording with a base plate and you're not simply recording with a video. You actually have both of them working together in concert, an algorithm that pulls them together so that you're getting a complete view, three-dimensional view of animal behavior in that social setting, in that home cage setting. So as I had mentioned previously, the specifications are that it's a full HD video. You're about 25 frames per second. What you see over the top is an infrared lighting panel. Each setup has its own PC Core i7 computer. And then what we actually do is we capture a small number of examples. We build classifiers on those examples. Those classifiers go on to capture a lot of examples, and it's a sort of a self-training loop from that. And then we test that classifier on the remainder of the examples, and we get these distinct behaviors, these distinct in-cage behaviors in the social setting. There are certain challenges is to keep designing these classifiers faster and to get enough quality annotations for it. So specific behaviors that may be unique to a particular phenotype, we need to identify those. We can do that when we get that video, and then we build the classifiers from that, and then hopefully, and in most cases it works fairly seamlessly, we can start to identify individual animals, distinct behaviors, and look at those animals discretely with respect to the other animals in the cage itself. And we get a menu that would look something similar to this with the behavioral annotation. You can see from the two panels, the two pictures at the top of the slide, each animal is identified individually. This is on an overlay. Obviously, an operator wouldn't need to see this. They wouldn't need to know which animal was which. But on its own, we can actually start to look at, after a period of annotation, we can actually see the periods of aggression. We can see which two animals were aggressive towards each other. We see when they're drinking. We can see when they're feeding. We can see when they're grooming. We can see general locomotion, so you can see if one animal is moving a lot more than the others. We can see the rearing, and we can also see the social grooming, so when they groom each other. The approach actually just involves using local trinary patterns. So what we would actually do is programming the features in the cage rather simply, so that we have we know where the water spout is, we know where the feeding hopper is, and we know where some of the features in the cage are. These can move around somewhat, and then we can spot the animals. And then when we know distinctly what the animal is doing, locomotor behavior, we can actually start to see, is it actually drinking, or is it just spending time around the water spout? Is it actually burrowing for something, or is there actually nest building going on? Is it actually sleeping, or has it actually expired? These are the things that we can start to look at very, very closely with this system. So our approach to this would be essentially using those trinary patterns, understanding the features in the cage, being able to recognize those, and then understanding that near the water spout is a region of interest, tracking the animal to the water spout, and then how the animal drinks, when the animal is drinking, and what animal in the cage is drinking. That all helps us to build the classifiers for this, and then that is supported through a certain amount of machine learning, so that after an initial round of annotations, we can start to have the machine record and tabulate these behaviors automatically. So here we have an example where we have a mutant in a cage with other animals. The mutant is in blue, and the other animals are the control animals. And you see that during the light phase, the mutant itself is not actually, it wouldn't actually be discernibly drinking a whole lot more from the water spout than the other animals. But you can see that in the dark phase, it is drinking considerably more and more frequently than the other animals in the cage and than it was in the light phase. So being able to look at those statistics and be able to look at those in comparison with the other animals in the cage and be able to look at those statistics and those animals both in the dark and in the light phase longitudinally is actually very, very important. And it gives us a different insight. So in this case, this was a particular metabolic mutant. It was conforming according to phenotype, but our ability to see that and our ability to quantify that was something that was a challenge before, but now we can actually quantify the amount of time it is actually spent actually drinking. Again, we would have had a video here, but you can see the behavioral overlays. So each animal is identified independently or identified individually. We can see the interactions between those animals. When we do the analysis, then it will show us what each individual animal is doing, the way that you see here, so that we can actually start to look at specific events that occur inside the cage and specific behaviors from each animal. So again, home cage, social setting, things are much, much different when you look at animals this way than previously, either looking at them in isolation or just sort of doing the cage side check or looking at them in specific functional assays. So in summary, the Crackit challenge met by Actual Analytics, the MRC, and the sponsored by the NC3Rs at the time. It brought the analysis into the cage itself, and it allowed us to score a range of behaviors automatically. And now we actually see that there are clear effects of group housing versus isolated housing, and clear effects of handling, and clear effects of what is actually happening in the vivarium, in the environment outside of the cage. And again, as I had said, it gives us a very different insight as to how we've been dealing with animals in the laboratory setting, previous to now. Here was a particular example from MRC that actually showed neurodegeneration, and you see that the distance traveled at 8 weeks, fairly similar between the two animals. But then we actually see that the neurodegenerative animal was doing a lot of climbing when we didn't actually expect it. So during the daytime, we didn't actually see that climbing, but after we had the ability to look at it when there was no one around, we actually saw that climbing behavior was actually increased in the HD animal, and then sort of started to normalize over time. but it was quite surprising to see it that in the dark phase that this animal was actually climbing when we didn't expect it to. And you can actually start to identify individual outliers. So you see our wild type control cohort is the thick blue line, and then the red and the green are actually individual animals. And we can see how close those individual animals are acting towards, how close those individual animals are acting towards the wild type controls. So the red animal itself is actually fairly, in terms of its pattern, is acting much differently than the control animals, and also the animal in green. So these individual animals are somewhat conforming to phenotype during the day, but in the evenings, the red animal in particular is an outlier. It was actually very, very sick. It wouldn't have been noticed, or it would have been hard to notice it during the daytime, but in the nighttime, when we analyze the data, we can see that it's not conforming to phenotype at all, and it's not even close to what the wild type controls are. So that actually gives us an indication of the welfare of that animal. It was an outlier, and would have, had we examined it much closer, would have been close to the ethical endpoint. And then looking at the current system that we have with the live telemetry and analysis, looking back at the previous slide, this animal in red, our ethical endpoints were essentially set. You can see that in the graph on the right, and then this animal hit the ethical endpoint and carried on beyond it. So we identified that outlier with the system, but not through observation, and we more than likely would have been able to identify it significantly earlier had we been looking at the system data. It was only later on afterwards when we actually started to compare the two, the observational data from the cage side check and the data that was being generated by the system, that we saw that this was indeed an outlier. Now, had that animal gone on, or even both of those animals gone on to subsequent behavioral, cognitive, or functional assays, then we might have had a problem. There would have been a possibility that the results may have been skewed one way or the other. And then when we look at this, continuing to look at this neurodegenerative phenotype as an example, the ethogram that shows the locomotor activity and the climbing activity over a 2-hour period, either side of lights on, so from 6 a.m. to 8 a.m. You can see that locomotion and climbing in both the wild type and the HD animal were actually very, very high when the lights were off. A little bit more, as you would expect, in the wild types during the daytime, but in the evening, the locomotor activity for the neurodegenerative animal, the HD animal, was actually considerably high, and that's not witnessed at all during the daytime. So almost no climbing at all when the lights are on, but when the lights are off, quite a lot of climbing. And also the amount of movement during the daytime would have been about what we expected, but in the evening, as the lights are off, you actually are almost entering a hyperactive phase. So looking at interaction of animals is obviously very important, something that we can do. So here's individual animals that we were looking at, and we look at the range of behaviors in those animals during the light and the dark phase. You can start to spot the outliers. You can start to spot those animals that were lesioned. You can see that the TBI animal is in the light phase is in red, and in the dark phase it's in brown or dark red or crimson at the top. So you can see how the animals reacting in different phases at different times. And you can overlay that data on top of each other so that you'll be able to start to look at the actual behaviors of these animals over a longitudinal period. So this was over 12 weeks in 3 models of trauma. And the amount of social interaction that those animals are actually doing during the dark and the light phase is significantly different, depending on what model that you actually had. So in light of the fact that I didn't have the videos to show, I think that does actually give a good overview of the system. And I'm hoping that if there are any questions that I can answer, I'll take them from you. But I really appreciate your time. And I think I'll end it there. Thanks very much. And also thank you to our collaborators with, obviously at Actual Analytics and at Naason Science, but also the MRC headed up by Sarah Wells, our initial partners at AstraZeneca, who helped us develop the system, and the University of Edinburgh, Queen Mary, and the University of Strathclyde. All right. Thank you very much.